In this lesson we're going to look at radioactive carbon dating. Now this makes use of a radioactive isotope of carbon called carbon-14, which will undergo a beta decay, as we've already seen in a previous lesson. So we've got a beta particle being emitted, and as you know when a beta particle is emitted, we move one step up in the periodic table, so the element that's now formed is nitrogen, and the half-life of this decay process is 5,730 years. So before we go on to talk about the plant and the mouse here, we've got to make a very important point about carbon-14 with respect to the atmosphere, and it is this, that the ratio of carbon-14 to normal carbon-12 is very small. It's approximately 1 to 10 million. So for every 10 million atoms of carbon-12, there is one atom of carbon-14. And what is important here is this assumption that the ratio of carbon-14 to carbon-12 remains constant. It has always remained at this 1 to 10 million. So how does radioactive carbon dating work? So first of all, let's talk about the plant here. What do plants do? Well, they absorb carbon dioxide from the atmosphere. Some of the carbons in the molecules of carbon dioxide will contain carbon-14. Most of them will be carbon-12. But as the plant absorbs that carbon dioxide into its body, the radioactive carbon-14 goes into its structure. Okay, that's to say the plant becomes radioactive. And we can say that the proportion of carbon-14 to carbon-12 in the plant remains the same as that in the atmosphere. That's to say 1 to 10 million. So that proportion will always be the same throughout the life of the plant. It will never change. It will always have this same ratio. So we say that while the plant is alive, the number of carbon-14 atoms in its body to the number of carbon-12 atoms will always remain the same. It will be the same as the ratio of carbon-14 to carbon-12 in the atmosphere. This will not change while the plant is alive. Okay, so this is constant while alive. So let's look at the animal now. The animal eats the plant, and the ratio of carbon-14 to carbon-12 in the animal will be exactly the same as the ratio in the plant, which will be exactly the same as the ratio in the atmosphere while the animal is alive. So this will be the same value, and this is important to get hold of. This ratio does not change in all living organisms while they're alive, and we assume that whenever they lived, that ratio was the same, whether they're living now or whether they're living 200,000 years ago. Okay, this is the same ratio. Now then, once we've made that assumption, we can then say, well, what happens when the organism dies? Well, when the organism dies, it stops taking in carbon-14. It stops taking in carbon, but it will stop taking in carbon-14. So the level of carbon-14 in its body will now start to decrease, because it will decay into nitrogen emitting a beta particle, and it will not be replaced by more carbon-14 because the plant isn't absorbing carbon-14 because it's dead, and the animal isn't eating carbon-14 because it's dead. Okay, so the activity then starts to fall, and as with all radioactive materials, it will fall in an exponential way, as we've already seen. So this shows the decay curve for carbon-14, and this graph indicates how the activity of an organism due to the presence of carbon-14 falls from the moment that the organism dies. So we'll assume that at this point here the organism dies, okay, and that its activity at that moment was 100%. So in order to determine the age of a sample, what we need to do is compare the activity of the sample when it is dead, that's to say the activity of our fossilized sample, with the activity of the sample when it was alive. which will be the same as the activity in any living sample at this moment in time. If we assume that this is the activity when the organism dies here, then if we have, for example, a sample of, maybe it's an insect that's been trapped in amber, okay, and you determine the activity of this insect and compare it with the activity of a living insect today, or any living organism for that matter, and you find that that ratio is 25%. That's to say, over the years, its activity has fallen from 100% when it died to 25% of that now, then we can go to our carbon-14 decay curve and work out the half-life. So let's do that. We're starting off with 100%. We've dropped by 50%. That's one half-life. And then we've dropped by another 50% of that to 25%. That's another half-life. So let's draw a line across here from 25%, and we'll draw the line downwards, and this will tell us the age of the insect. Okay, we know that the activity will fall to 25% in two half-lives. That's 50%, and then half of 50 is 25. And so if the half-life of carbon is 5,730 years, as we mentioned earlier, then the age of this insect will be 2 times T half. Just spell that out again. We've got one half-life to 50% there, and then another half-life to 25% there. That's 2 half-lives equals 2 times 5,730 years, which will be 11,460 years. So we can say that that insect was flying around about 11,500 years ago until it unfortunately got stuck in a glob of tree resin, and that was the end for the insect. Now, just to finish, there are a couple of important points that I'd like to make about this dating method. As you can see from this graph, when this sample is relatively young, that's to say less than about 20,000 years old, then it's not that difficult to establish the age of the sample. And the reason for that is because the exponential curve is still relatively steep. Okay, it's falling quite rapidly. But if you go beyond 25,000 years, for example, between 25 and 50,000 years, then the graph starts to flatten off. And for that reason, it becomes a lot harder to establish the age of a sample. If you go beyond 50,000 years, then really this method of carbon-14 dating becomes ineffective. Its half-life is really too short to establish the age of samples that go beyond that time period. And the other thing, as I said before, the process of radioactive dating using carbon-14 depends on the fact that the ratio of carbon-14 to carbon-12, this 1 to 10 million, has remained constant during that period of time over which radioactive carbon dating is effective. We must assume that it should have remained constant at least over the last 50,000 years. Beyond that period of time, the method really ceases to be an effective dating method.